engaged, and they can't hear anybody that doesn't talk through a mic. So,
all right,
take it away.
Yeah, well, hi everyone. So I'll fully admit this isn't really an open problem in the sense that I think we're going to come to a great solution right now, but I think it's a common annoyance at least. So let me describe it and see what people think and if they've encountered this kind of thing themselves. So basically in planning, right, you have a set of feasible solutions. These satisfy your hard constraints, complex set. And each solution can be evaluated with multiple objectives. Let's call them F1 through Fn. And in the talks this morning, we saw several different objectives already, right? Someone was talking about the probability of collision in the motion planning problem with uncertain obstacles. There's path length. I heard jerk mentioned. There are things about the bending energy or the curvature, or there's a whole set of different objective functions we could use. And generally you'd like to minimize them all. It's good to minimize them all, but they compete with one another. And so you have necessarily trade-offs. So what do you do? I'll give you a few ideas on what you do. I think the second one is the one that people most commonly use in this case. But the first one is maybe the theoretically potentially most appealing, which is you find the Pareto front, right? So that's the set of all the solutions that are not dominated by another solution. So just to be clear, so we know what we mean with dominated, it's that a solution S is dominated by another one, S bar, if that S bar has a lower objective value for all the objective functions, and there's at least one where it's strictly better, right? Otherwise, if they're just the same for all, then we don't say either dominates. That's hard to compute generally. And even if you did, you're not done, right? Now you have this complicated subset of the feasible solutions, and you still have to pick one from that subset, right? So it's not like the Pareto front's the holy grail in some sense. You still don't know the answer at the end. I think the most common option is linear scalarization, where we take a weighted sum of the objective functions. And the key drawback to this is, how do I choose the weights, right? Someone has to come up with the weights. And the other thing, and I'll only mention it briefly, is that it's not Pareto complete. That means you might find the minimizer for a particular set of W's, but there actually is another solution that dominates it. That's what not Pareto complete means. Okay, another option, which I think people do, myself included sometimes, is, okay, I've got too many objectives, let's put some in the constraints, right? Take some of the objectives and turn them into constraints of the form Fi of S is less than or equal to Bi. And I guess my question there is, have we really achieved anything? I still have to pick the right-hand side of the constraint. So I don't have a Wi, but now I have a Bi instead, right? And then there's alternate methods of scalarization, so that actually solve this Pareto complete idea instead. So instead, you could solve minimize over all the solutions S the maximum of the weighted objectives. And this, again, you have this problem that how do I pick the weights? But now at least this is Pareto complete. If you find the optimizer for it, there's not going to be a dominating solution out there. So anyway, this is my long preamble to say, what do we do? How do you, and maybe just even, it would be interesting to hear from different people, how do you proceed in this conundrum, right? Of multiple objectives, and you need a way to deal with them. And just my last thoughts on things that make this hard or interesting is, generally these objectives have different scales, different units, and so they're not even comparable. How do you compare the probability of collision with the path length? 7 times the probability of collision plus path length, is that good? I don't know, right? Also, even if you knew, I care 2 times more about probability of collision than path length, does that mean I pick the one weight 2 times as large as the other? The translation isn't that clear. Is there really a single set of weights, or is it just specific to the particular task and context that we're kind of thinking about? And then also this idea of kind of prioritizing or nesting optimization. So I pick an outer objective, and then optimize that, and then optimize the second one subject to a constraint that I found by optimizing the first, and so on, like something like this. So anyway, that's the end of my preamble. I'd be interested to hear people's thoughts on this.
I'm going to do my best to get people in the order that I see their hands get raised.
Hi. I think this is a great problem. I don't have an answer to it. I just have an observation to make. This seems to be very similar to the alternative. If you decide what the weights are, then it looks very similar to the alternative direction method of multipliers, the ADMM, which has, in the past decade, people have done a ton of research there. They have centralized solutions. They have decentralized solutions. There exist analytical gradients on how to kind of accelerate the convergence rate. This is exactly the form of distributed optimization. You don't necessarily have to say it in a distributed way, because even you have one agent, you can do something like divide and concur to accelerate the convergence of your optimization. This is, just one takeaway, that the problem you describe, the problem formulation you describe, if you find those weights you said, then it's, ADMM is the way to go. One very good way to go.
Yeah, interesting. Okay.
Over here, surprise. Nope.
Yeah. Oh, hi.
Question or comment.
I saw another mic.
One thing that I think may be interesting here is, if you imagine, okay, the parameter space you're optimizing over, that is, what do I want to say? Nope, I messed it up. Consider the weight space, and then for certain collections of weights, they all lead to the same Pareto optimal, right?
Yeah.
So there's an implied cell decomposition in the weight space, right? Which is an interesting kind of computational geometry problem, perhaps, in different sorts of contexts. And I don't know what it ends up looking like, but that's one possible thing that one could study if they haven't already. And then the next thing that might happen is, imagine you have a system where the priorities are a dynamical system. So the weights change over time as the system gets used. Some things might become more important, like the price of gasoline goes up. So now you want to optimize gasoline instead of how fast you can get somewhere and stuff like that. And then the size of those regions start to matter, right? Because maybe there's big regions of weights over which, that's like a very stable, you can make like a dynamical system stability kind of analysis over weight space. Anyway, just some extra thoughts there.
No, it's a great, so what you say is actually, it's exactly right. So we've done a bit of work on identifying what we call equivalence regions, which is just the set of all weights that lead to the same optimal path, right? Or for which the optimal path is the same. And there are some nice properties, like that set's convex. Computing it, though, and the extent of it is not easy. I mean, Nils, who was a PhD student with me, is now a postdoc at Delft. He's been doing more work on that than, is more of an expert on that than me, but that's definitely a great observation. And I don't know exactly how it helps you in solving this right now, like, yeah. No, but thanks. Yeah.
So one potential issue I just thought of is when a situation might be Pareto, let me see, part of the Pareto front and possibly found when you make the weighting, but still isn't good. And I was thinking the hypothetical, let's say you have there are two constraints and they compete, and you can make one of them good and the other one bad, one of them bad and the other one good, or you can get them both really mediocre. It's possible that if you weight them both the same, you will end up selecting the solution that is mediocre in both of them, even though really it's okay to have one of them be quote unquote bad, but having them both be really meh is actually a strong negative. How do you account, and I'm just thinking, how do you account for that